Great. Hi, everybody, and thanks for joining tonight's presentation on the future of solar energy, presented by Maria and Joe Barry from the National Renewable Energy Laboratory. Maria is the Mid-Atlantic Renewable Energy Association. We are an all-volunteer nonprofit that depends on donations from our supporters to bring these timely and relevant topics on renewable energy and sustainable living. After tonight, we upcoming presentations on backyard composting. This is kind of a hands-on lesson for turning kitchen scraps and yard waste into valuable compost, and that is on June 28th. And then on July 26th, we'll learn how we are integrating renewable energy into the grid. This is a very important topic. It's one thing to have renewable energy. It's another thing to get it to where it's needed. And that will be with Ben Kroposki, also of the National Renewable Energy Laboratory.
I'm in.
So with that, Phil, if you want to introduce tonight's speaker.
Yes, thanks, Tom. Just a reminder up front, during the presentation, please mute your microphones, and you can enter questions into the chat box. And at the end of the presentation, we will be asking your chat questions to the presenter. Tonight's presentation will be recorded. And now it's time to take you into the future of solar energy. We're pleased to have tonight Joseph Barry, a senior research fellow at the National Renewable Energy Laboratory, or NREL, where he is researching the next generation of solar cells. He is a principal investigator on the NREL Department of Energy Solar Energy Technology Office's Advanced Perovskite Cells and Modules program, as well as being the director of the U.S. Manufacturing of Advanced Perovskites Consortium, a fellow at RAISE, a joint energy institute between the University of Colorado Boulder and NREL, and an associate professor of physics at the University of Colorado at Boulder. Dr. Barry is concerned with developing solar panels which require less energy to produce, or what's called embodied energy, lower cost to produce, and or also have longer producing life. In his presentation tonight, he will examine existing cell and module technologies, highlight some of the current concepts to improve these different energy figures of merit and ultimate cost. In particular, he will address advanced low-cost tandem technologies incorporating established, that is, gigawatt scale, and our next generation of absorber materials, including metal halide perovskites. Welcome, Dr. Barry.
Well, it's a pleasure to be here, and thanks very much for the invitation. I will see if I can execute on the sharing of the screen. Does that look okay?
Excellent.
All right. So when I present, the first thing I really like to do is to highlight a lot of the people on the team that I lead at NREL. And here are some of the faces. The folks with the red circles are recent folks who've matriculated onto bigger and better things, professorships and new research jobs. But we've got a lot of people doing a lot of hard work at the lab trying to develop some of the technologies I'll be talking about today. I also want to take a little bit of time to thank some of the partner companies that we work with. You know, obviously we do a lot of work in the lab to try to develop the next generation of technologies, but that work really has to be translated from the lab to commercial processes that result in products that people can buy and install. And we are working with a whole cadre of different perovskite manufacturers as well as supply chain entities to work at that, as well as a couple key university partners, University of Toledo Wright Center, University of North Carolina Chapel Hill, and University of Washington, particularly their clean energy test beds. So in addition to University of Colorado, where I work, in the SLAC National Laboratory out in California that's associated with Stanford University. All right, so as was kind of indicated in the abstract, I wanted to make sure that we're kind of clear on the notion of the energy balance sheet for different technologies. And this idea of embodied energy is really the energy that we dump into something to produce it to begin with. Most people don't realize that that can be a significant fraction of the overall energy of a product. The current kind of canonical example is the cell phone. Your cell phone takes about 75 times more energy to produce than you will use it over the course of, say, a 3-year lifetime for that product. And so finding ways to lower the embodied energy is a really important thing in terms of trying to mitigate the CO2 impacts. Now, that embodied energy, as I kind of indicated, is compared against the primary energy consumption. And again, in the case of a cell phone, that's a device where energy is really at a premium because it's portable and so on and so forth. But that really means that the energy over the use of its lifetime is pretty minimal in compared to that embodied energy. For technologies where we're generating energy, like PV, we have this concept then of an energy payback time where we look at the embodied energy and we compare that to the energy that is produced. And that's what's shown up here in this simple little graph, with the notion that, if it took us essentially a certain amount of energy to produce it, and it takes me, say, in the case of a PV device, we'll be talking about this explicitly, if it takes me 2 years to recoup the energy that it cost to make that device, or put another way, I need to basically field a PV device for 2 years before I've made enough energy to produce it again with no additional energy from any other source. That energy payback time is really kind of a critical break-even point. And then beyond that time frame, right, then we have an energy return on investment from that particular technology. There are other kind of considerations, like I mentioned in the context of a phone, portability, but for energy generation technologies, this idea of dispatchability, providing energy when we want it, where we want it, and also energy density, right? Things like fuels have high energy densities, and those have a value proposition all of their own that is part of the calculus that we want to do when we're thinking about energy technologies. But if we look at solar technologies generally, there are a number of different solar technologies. These are the 3 primary ones that we typically think about at the National Renewable Energy Lab: solar fuels, concentrated solar power, and photovoltaics. Now, of these 3, 2 of them are really things that are deployed, as you can kind of see here, and solar fuels is what we have here. The idea of solar fuels is really an elegant one, which is the notion of taking direct sunlight and converting it into chemical energy in bonds, essentially. Either creating chemical bonds that we can use as a fuel, or driving directly with the chemistry that we're exciting a system like I've shown here, a fuel cell type configuration, and then getting the electricity from that. So, electrolysis is a great option for basically then releasing those kind of, or generating and releasing those kind of chemical bonds. But we are trying to do, as you can kind of see here with all the circles and all the little arrows, 5 or 6 really hard things simultaneously. In contrast with the PV, right, we're trying to simplify that, and we're trying to make things a little bit more streamlined. But this does have the ability to kind of generate things like fuels, which have some advantages in particular contexts with, say, dispatchability. If we look at, is it going to advance? Solar thermal, okay, concentrated solar power is something that we've known about for a while. It does have integrated storage. The other thing that people like is that you're using so you have all these mirrors, you have what they call a heliostat or a receiver where you focus all the light, make something very, very hot, and then you use that thermal energy and you convert it to electrical energy with a generator, right? With essentially a steam turbine. One of the advantages here is that you can really do things like combined cycle, which improves efficiency, but you can also use dual fuel. So you can use a solar array during the day, and you could cross this over to, say, natural gas or some other fuel source to do the heating when you need it, or when, say, the solar resource isn't as available. The catch has been that these kind of installations really do require really good unobstructed solar light. That is to say, things like clouds really impact the ability of these kind of facilities to be very, very efficient. There's also considerations of kind of soiling, right? You need to be relatively, the question of how large you need to be, right? Scale actually shows up here. You need to be big enough, but you also, being too big creates its own set of issues for you as well. There are new technologies that people are looking at there, but the economics of these kind of systems end up being pretty challenging for the most part. Then we come to what we're going to focus on today, which are really kind of photovoltaic cells. So the idea here is a direct conversion of a photon from the sun into essentially an electron and hole. And those two particles then, right? So it's kind of the inverse of what we do when we do an LED. In a light emitting diode, right? You combine an electron and a hole and you generate a photon. Here we're going to take a photon, create an electron and a hole, and those two things basically represent electricity that we can harvest directly. One of the key features of these types of systems, they're often stacks like I've depicted here. They're based on semiconductors, and I'll talk a little bit about what that really means to be for a material to be a semiconductor. We can do a lot of engineering of the materials and the semiconductor. Some challenges for the technology are dispatchability. I'm not going to make the mistake of, and I'm sure that most of the folks in the audience would certainly recognize the notion, right? People say, oh, well, the sun only shines in the day, during the day. Well, the sun is always shining. Whether or not you have access to it is maybe a separate matter. But if you're a ground mount PV or say a rooftop installation, yeah, certainly you only have access to the sun when the earth is essentially facing it. But that does create some challenges with dispatchability. In addition, because we're talking about semiconductors, these are the same kind of materials that are enabling us to have this conversation over the internet. It's the thing that drives all our computers, cell phones, et cetera, et cetera. That does mean that these materials have some, stability and durability challenges when we think about putting them outside for, decades at a time and expecting them to perform their primary function. Another challenge is kind of, the existing electrical grid infrastructure in the sense of how we, given the periodicity of this resource for land mount, what the implications are in our ability to, say, deliver that power from where we've generated it with the panels to where it is we want to use it. Again, residential has some advantages, but for kind of more general use in the commercial space, when we're thinking about industry, that also creates some challenges. In terms of what kind of research we're doing, the device physics of these has been pretty straightforwardly understood for some time. The devil is really kind of in the details of how we execute what device physics we're trying to do. There are some ideas about technologies and approaches to capture energy in a PV-like way that really exploit quantum mechanics in new and different ways that can improve upon some of the efficiency limits that I'll show you here. I'm happy to talk about that, but that ends up being quite technical. So a lot of the research is related to how do we execute the device physics we want with materials that have superior performance along one of a couple different axes. There are also questions about things like the power electronics and the other kind of paraphernalia that come along with a solar cell to basically turn it into a module, and then the module tying into the grid, things like inverters and so on and so forth. There are a lot of people who are interested in essentially what we call high specific power, which is a high weight to power to weight ratio for applications like, for example, satellites or low Earth orbit kind of drones and things like this. So this is an area that people are pretty excited about, and that also has some implications for residential PV, because if you can make these systems lighter than what current systems are, you can maybe think about integrating them into different kind of applications that would otherwise have been prohibitive, say into a window or into other kind of devices, say awnings and things like this. All right, so given that all solar cells are semiconductors, this is what's known in the business as the chart. This is the best research cell efficiencies over time And there's a lot going on here, so don't worry too much. I'll be breaking this down in a little bit more detail. But this also indicates that efficiency is a key metric for a solar cell. And again, the cell is just the basic component that's doing, say, the real operating of turning the light from the sun into electrical energy. We need to basically then chain a whole bunch of those together to make a module that's kind of the unit that you find on, say, the top of your roofs. But if you look at that, there are solar cells that started around shortly after 1975, and you can see that this chart goes up to, actually it looks like I've got a little bit of an older chart, but yeah, 2022. And there's a lot of different technologies, and some are way, way more efficient than others, as you can see. But you'll notice there's a little bit of a confluence around here, and we'll talk a little bit about why that is, and how it is you get into, say, this rarefied air up here of very, very high efficiency systems. But I wanted to make sure that we're all kind of on the same page with respect to, the fundamental properties of a semiconductor. If you take an atom by itself, it's got a discrete set of energy levels that are dictated by the details of that atom, right? Of its electrons, its nuclei, and so on. One easy example is something like neon, right? Neon gas has kind of discrete states, and it emits from the fact that basically you can excite an electron from the ground state to this upper state, and when it relaxes back down, it'll emit a photon, and that's how we generate light with, say, a neon light. Now, we can take atoms and we can put them together in the case of chemistry, and we can make molecules. And when we do that, these kind of discrete energy states start mixing and bifurcating, and we get a manifold of states. Now, if we do this kind of chemistry and organization of the atoms in a way that's periodic in space and tailor it, we generate essentially continuums of states, and for some materials, we'll have these gaps between different states. Now, keeping in mind that this lower state is the ground state, and this upper state here in blue is the excited state. So the electrons in these systems all want to stay in the red states, but when we excite them, they can move up into the blue states. But they can't occupy these gap states. And here I've shown the same kind of breakdown that I'm just walking through. And a semiconductor is a material where we have this discrete band of disallowed states. So we have essentially electrons filling all the valence band states, or these lower states, and we have unfilled states that the electrons can be excited to, which is essentially what we call the conduction band. So we can leverage this kind of particular electronic structure to do photovoltaics, right? And to do a lot of different tasks. In fact, we leverage the same thing for light emission, right? Because I can throw an extra electron in here, let it relax down to the valence band, and when it does so, it can emit a photon. Or in the case of PV, as we've shown here, I can absorb a photon, take an electron from here, leave a hole where that electron used to be, and put the electron into the conduction band. So that's kind of what we're leveraging in the case of a photovoltaic material. All right, so this is the device physics of a solar cell. We have semiconductors where we can manipulate this electronic gap in the material in a way that we can tune it so that we can decide which photons will absorb. If a photon has an energy that's insufficient to basically take an electron out of the valence band to the conduction band, that means that it's functionally transparent, the semiconductor is, to those photon energies. And that's a really important kind of thing. But once we have an electron in a hole in a semiconductor, and in this little stack that I've shown again here, the goal is to extract it before we lose it, right? So every photon that we absorb, we generate this electron in a hole pair. We want to extract them before we lose them back. In the best case scenario, it'll recombine and generate a photon, but oftentimes semiconductors aren't as perfect as we might like. So they can recombine, and basically that energy is lost to thermal noise inside the system. Now here I've also shown what happens if we excite above that gap. We very quickly thermalize the electron down, and that's again heat that's lost that we can't use as efficiently as we might if we just basically tuned the photon energy to the band energy here. All right. So that's Semiconductor 101. That's how all of these technologies here work. And it's also why, if you look at the names of the different technologies, there are things like gallium arsenide, CIGS, all these different names that you see over here, silicon. Those are all the semiconductors that are the basis of the technologies that we're talking about. But if you break down of all these different PV technologies that have made their way one way or the other to the chart, which ones we see really out in the world, it's a pretty exclusive subsection. The first is silicon, and this is what you find most commonly anywhere across the world, or indeed in the US. And if you look at this, silicon solar cells have improved in efficiency modestly over the years. And there are two different types. There's monosilicon, which is primarily what I'm going to focus on, and there's what we call polycrystalline silicon, which is both cheaper and slightly less efficient. But the key thing here is that when we look at how much time it takes us, right, given the efficiency of these devices, to recoup the energy that it cost us to make the devices to begin with, it's somewhere between, you can maybe drop this 0.5 off here, but between 2 and 3 years to get the energy back that it cost us to make the device to begin with. Or put another way, if I spend that energy, I have to wait 2 years before I can make another batch of silicon solar cells without using any other resource besides the silicon devices that I made to begin with. Now, we have other materials like gallium arsenide, and these are really the best solar cell materials. They're much more efficient, right? They're 6%, so from 26 to 30%, so 4 absolute percent efficient, more efficient than silicon. But if you look at the energy payback time, they're 4.5 to 5 years. And that's because the energy that it takes us to do all the refining of the materials and everything else is just a lot higher. And so it turns out, we'll talk a little bit more about this later, but these materials are used, but they're used on things like the Mars rover. The other commercial technology that we have at kind of gigawatt scale is CAD telluride. And First Solar, which is a US-based company, their headquarters, I believe, is in Toledo, or just outside Toledo, Ohio. This is a 22% technology, so not as efficient as, say, polycrystalline silicon or certainly single crystal silicon, but the energy payback time is a fraction of a year, right? So 0.8 to 0.9 years. So it's much, much better from the perspective that the energy cost that it takes me to manufacture it relative to, say, a silicon module. And this is one of the reasons that while its efficiency is slightly lower, its cost is better. In addition, there are some other considerations as well, but this energy payback time is a real critical consideration. So for the technologies that I work on most of my time, we're looking to basically change from that 0.8 to 0.9 years to 0.1 to 0.3 kind of years for energy payback time with new technologies, namely these metal halide perovskites. And you can see here, I've included a number of other technologies that haven't succeeded because they really haven't achieved efficiencies that are sufficient to be kind of commercially viable. But this yellow line is the perovskite, metal halide perovskite line, and you can see that it's quite impressive here in terms of its efficiency, with efficiencies topping out at 25%, which are starting to rival single crystal silicon, but really take a fraction of the energy inputs to produce. So all of that's really great, but those are all research cells. So those are teeny tiny cells that we make in the lab. Those are not big panels that we put on people's roofs. This is the efficiency chart for the record efficiencies for modules, which are what we put on people's roofs, i.e. combinations of cells that we construct one way or the other. And a silicon module right? Record silicon module at large scale, and the yellow or the color here, right? The yellow or orange indicates the size of the module. A silicon champion module is at 22%, 22.8, it's almost 23. CadTel, it's 19. And gallium arsenide is 25, so it's significantly higher, but again, at much, much greater cost. And then we have perovskites at 17.9, so almost 18%. But I'll indicate one important thing, which is this hockey sticking here, right? And it turns out if I had shown you this same graph 2 years ago, this would be the only point on that graph. So this is really accelerated because we've really addressed kind of the efficiency component of this. And this is a little bit of a zoom in here so that we can take a look. But if you really want to be a real PV technology and you want to address the challenges associated with enabling a module, you need performance or efficiency. You need also the manufacturability, which means speed and yield of production. And then you need stability or reliability, which is the last component. And I want to, and we have this article that's, I'm pretty sure it's open source, and you can find it where we walk through some of this stuff. But for some perspective, right, the first practical solar cells were reported in 1954. And this was, going to be the thing that solved all of our problems, and with any luck still is. But the way that they evaluated the efficiency that I've shown you in these last couple graphs would not be okay to report today. More importantly, when we think about efficiency, we test efficiency in what we call standard test conditions, right? We do it in a lab in a way that's very controlled under a very fixed set of conditions, but that's not how solar cells really operate in the real world. In the real world, right, they're outside and there's variable cloud cover, there's changes in temperature which impact the performance of the solar cell, and indeed the spectra can vary from different locations on the globe as well. And when you account for all that variability, we have a figure of merit we call energy yield, which is taken from actual modules actually fielded to know what the yield of energy production is. It's got to be related to that efficiency, but it can vary pretty dramatically from just that raw efficiency number because of the details of the cell's ability to harvest energy, say, through the course of the day. That efficiency is kind of the number that you get at peak sun, high noon in the middle of the day. But if, say, a technology like CadTel does better in the beginning of the day, right, at low light in a way that silicon doesn't, and in fact, that's a thing, that can impact the energy yield. So when we talk about the energy payback time, we really are comparing that against, that efficiency number or that idealized kind of energy yield to what it is that we've spent in terms of making that device. So I thought it'd be, so silicon is the technology. And so it's an interesting question to say, well, what is really driving that energy cost? Like, where is it that we spent all this energy to make the thing that we don't spend in, say, something like CadTel and some of these other materials? And it turns out that it really is in the making of silicon as a semiconductor. This is a schematic that kind of shows the basic process. And this just involves a lot of energy. You have to basically do a lot of melting, smelting, and burning to basically get silicon into this metallurgical grade silicon and then get it refined. There are also some kind of deficiencies at a very basic level of silicon relative to some of the other semiconductor materials that we like. But if you think about it, silicon is really what makes computers and everything else go around, which really means that we understand a lot more about silicon as a semiconductor, which really creates a lot of advantages when we're trying to use that semiconductor for whatever task it is, whether it be solar or whether it be ICs and computer chips and so on and so forth. So given how we develop silicon for ICs, what happens when we make that material is we get this metallurgical grade silicon where we've already spent a bunch of energy to refine it, but then we melt it down at high temperature and we pull it into big, massive single crystals, which we then subsequently cut up and we wafer into these kind of canonical things that you've seen probably in Intel ads and in other things. And it turns out that when we're wafering like this, they really do this with diamond saws. And this means that you're essentially cutting these things apart. And whenever you cut a piece of, say, bread, right, you get crumbs. And just like bread, with silicon, you get a lot of crumbs. But in this case, those crumbs are high value, high embedded energy semiconductor that you're essentially throwing away. Now we can recuperate some of that, and so we can get back some of that energy, and it's not entirely lost. But the key thing is that the wafer thickness that we cut it down. Then, given the way that we cut it, our semiconductor has a lot of problems that have to be addressed on those surfaces. So we clean that up, and we're left with a wafer that's kind of on the order of 150 microns thick. Now, in contrast, something like CAD-TEL, which has a much lower embodied energy and much shorter energy payback time, uses something like 0.5 to 5 microns worth of material. So that's part of the cost, but also a lot of these other semiconductors use a lot less energy to make them than what we use in the case of silicon. But okay, we've got our wafer. It's a high value, high purity kind of thing, really great semiconductor. And then we're going to put it into a module, and that involves putting all the solar cells together, chaining them up, linking them together into strings, and then we have some paraphernalia that we put around it. We've got some lamination layers, we've got glass front sheet, we've got back sheet that could be glass, or it could be some other kind of polyvinyl thing, or another kind of polymer, multi-layer polymer. And then we've got a few wires and junction boxes to basically help take the electricity that we're generating in the panel out to the real world. Now, we can look at that from a CO2 or energy perspective. And if you look at that and where you've essentially spent CO2, and in this case, CO2 is equivalent class to the energy, you can see that the energy is dominated by, and the electricity of the module is really dominated by the wafer and the cell, right? So this is really the silicon component. Now, all the other paraphernalia that we're putting around it, right? That is to say, the stuff we're putting around the semiconductor to make it into a module is pretty minimal in terms of cost. There's a few other things like transport, and there's even some end of life budgeted in here. And this was done in a recent review article that was just published last year. So, and this is for a pretty standard silicon module that's produced in China, which is where a lot of these systems are made. But if we think about next generation silicon modules, and that's what we're representing here, they're moving from kind of having these wafers to having essentially slices of the wafer so that they can reduce essentially the dead space in the module, right? And improve the overall kind of fill of the semiconductor, and to do some things with managing how the electrons and energy flow through the module. And we also see, they both have aluminum frames, they both have the glass front sheet, but now really people have been starting to move to these glass back sheets and things like bifacial. And I know that this is a topic that's super interesting. So I wanted to spend a little bit of time on it. Glass really enables bifacial, and the idea here is that you get not only the sunlight that's coming directly in, but you also get diffuse scattering from off the ground, things that are essentially, again, diffused by clouds or other sources that can essentially be harvested on the backside of the module. It also enables, concepts like this that's shown here, where you could mount these things vertically in a highway, and you could enjoy essentially illumination throughout the course of the day from the different sides. And that has some advantages. And it turns out that as a practical matter, when people have done the evaluation, it looks like you get kind of on the order of a 3% bump in the overall energy yield, which equates loosely to a module efficiency that's moved, say, if your module was a 22% module, to a 22.7% module. So it's pretty minimal, but you could also argue that a lot of the things that have been done so far where this data has come from haven't really been optimized for these kind of geometries. So you might be able to get 5%, which, is more on the order of 1% absolute, which on the one hand is impressive, but is something where, anytime you advance a technology and you change it, Now you open up your questions about, say, the reliability, stability, as well as the manufacturability. Can you still make that at the high volume perfectly every time with the high yield? But for, bifacial, people have been doing this, and you can look at the CO2 equivalent for a European bifacial module, and you can see that the carbon footprint is about a factor of 2. Now, a lot of that comes from the fact that where you make the module does impact its carbon footprint, but you can still see that even though we have 2 glass sheets in this module, the energy is really dominated by this green component here, which is the silicon, in a way that is distinct from what we have for some of the other technologies, namely polycrystalline thin films, which are things like CAD-TEL and perovskites that I highlighted already. So the CO2 equivalent is a useful metric, but at a fundamental level, you're still spending a lot of energy on the silicon, which is why I highlighted the curve, because, any silicon that's wasted really is energy that you wish you hadn't spent. So when we think about thin film technologies, they really do have some kind of critical advantages. First off is the thickness, so the overall amount of material, but perhaps more importantly is that we don't waste any. This shows kind of a blow up for how we make a thin film device. And in contrast to making this, boule and cutting up the wafers, you deposit this material directly onto a glass kind of continuously. And then you actually do laser scribing and other removal techniques to define the cells on that large plane. If you look up, First Solar has a lot of nice YouTube videos that can show you exactly what that manufacturing process looks like. And that really contributes, all these things contribute, the speed of manufacture, the cost of the materials, the total amount of materials used, to this lower energy payback time. And it also turns out there are some advantages from an energy yield perspective because of its performance, say, under different kind of conditions due to different weather or different kind of configurations where you might essentially mount them. So this is a little bit of a technical graph that shows what we call the detailed balance limit for a single junction photovoltaic device. So this is set by thermodynamics, and if you recall, those of you who are physicists and chemists, right? Thermodynamics is one of those thermodynamic laws. You daren't break those most of the time. And at a very basic level, when we think about concepts like bifacial approaches, we are still fundamentally limited in more or less the same way. We can modify this slightly, but only very slightly in a way that actually would be difficult to depict on this graph. There are other things that we can do, like, say, solar concentration, where we use reflectors to increase the, very much like what we would do in, say, solar thermal, but instead of having a receiver where we're heating something up, we would still put it onto a solar cell. That can improve the efficiency again, but again, the advantages there are relatively speaking around the margins until we go to very, very large concentration, and then we create other kind of challenges for ourselves. So how do we really beat this kind of limit? And again, you can kind of see where, say, technologies like CAD-TEL, because it has this very low embodied energy, even though it's a very small fraction of what it's entitled to, can compete against silicon that's actually doing pretty well. So any of these technologies up in this blue region are doing quite well. And you'll notice that perovskites and gallium arsenide are actually quite high up in these as well. So how do we beat this limit? Well, if you think about where our fundamental losses are coming from, they're coming from this compromise of, do we take the photon in or do we let it go through? And if we take the photon by lowering the band gap, how much do we create in terms of thermalization loss? Well, if you think about it, then if I had a single color for the light from the sun, I could make an 85% solar cell pretty easily if I matched it to the color that the sun was emitting if it was just one wavelength. So it really is about the spectral content that creates this limitation. So if I can slice the solar spectrum up into chunks by using multiple cells that each basically take a different slice, right? I can take these high energy blue photons, which would have created a lot of thermalization loss in, say, this lower gap cell. I can take those off the top. They don't create that thermalization loss. the ones that aren't energetic enough basically go through to that second cell and to the third cell and to the fourth cell. And it's this strategy that allows us to get up into these extreme areas of the efficiency chart. But as the graphics here indicate, these really are the best solar, and this kind of shows you a triple junction device like what I showed before, and how the solar spectrum is actually sliced apart by the different subcells. So this is the kind of thing that's often implemented. And again, it's one of the best technologies not on the planet. Turns out, per square meter, it's kind of the cost of a Maserati. But, if you're going to have a rover on Mars, it's totally a viable technology. So now I want to switch gears slightly to talk a little bit about perovskites. Perovskites are a really, really common structural motif for minerals that are common in the Earth's crust. Different oxides, barium titanate, iron, bismuth iron oxide, all these kind of things. And something on the order of 80% of the minerals found naturally are perovskites. So those are not relevant for solar. But they have the same structural form that I've shown down here of the materials that are. The materials that are relevant for solar are what we call the metal halide perovskites. And again, they have the same kind of crystallographic structure, the basic, kind of the way the atoms are assembled, and the same chemical formula. But one of the things that's unique about these is that these materials are synthetic in the sense that they don't exist in nature. And one of the things that distinguishes them is that they have the metal, and here I've shown lead, but there are a couple choices we can make for the metal center. But they have these gray things that can actually be molecules rather than atoms, although we can use things like cesium at these gray sites as well. But they are a combination of organic and inorganic for the most part. Now, these materials have been around for a while, and they were first found by David Mitzi, and he was interested in them for transistors. But then more recently, like I said, a little over a decade ago now, people realized they were really, really interesting for the solar task. That is to say, they were semiconductors, because we knew about them from David Mitzi for things like transistors, but they weren't sufficiently better than, say, the incumbent technologies, namely amorphous silicon in that case, for transistor applications. But for solar applications, they're way, way better than a lot of the other materials that we've looked at. So they absorb light really, really well. We can also tune their essentially optical absorption, or that electronic gap that we talked about earlier. And these graphs just show that. And you can see essentially films that as we change, say, out the red dot here, which is our with different options out of this red box, that corresponds to that, we can tune essentially the color of these materials, and that again corresponds to the optical band gap. So they have a large degree of tunability, they interact well with light, and they do a lot of the other kind of very basic things at a semiconductor level that we need to do to basically absorb photons, create electrons and holes, and extract them out effectively. So this is where we are from a research cell perspective. Again, these are the most efficient polycrystalline thin film in under a decade, so that's a really important thing. But as a result of that efficiency, efficiency isn't the issue anymore. And so it now becomes a question of, can we make these things reliably and stably, and can we make them at large scale? The other line here that I wanted to also highlight is the silicon perovskite tandem line. So I said that tandems and multijunctions, by slicing up the solar spectrum, offer an opportunity to get to higher efficiencies. So you can see that the combination of a silicon and perovskite devices coupled together has now exceeded what can be done with silicon devices alone. And that starts to put us in the regime where these other multi-junction technologies are. So, okay, that all sounds good. But the best part is that these kind of record efficiencies are coming from materials, semiconductor materials, that are essentially solution processed. And here I've shown different ways that people have done and used to produce high efficiency perovskite solar cells. Spin coating, dip coating, blade coating, all of these are highly processable via solution and can be done at large scale. And here I've shown one of the pilot lines in a Kodak facility that's being targeted for basically producing these things at high volume. But of course, right, it's one thing to make the small cells, and I showed you that hockey stick on the module line. So we're very quickly climbing the ladder of how is it we make a lot of this stuff very, very fast, very, very rapidly. And when you think about what that means, because we have essentially a material that has low embodied energy, we can tune the details of the band structure. We can make all these different tandems in a way that is kind of potential. Well, we think it's transformational. So here I've listed kind of, we can make perovskites of different types and pair them together to get over 25%. The silicon perovskite tandem is now at 29.5%. CIGS tandem, which is another thin film technology, at 24.4%. People have doing plastic solar cells, organic solar cells with perovskites. CAD-TEL with perovskite is one that people are kind of looking at, but maybe doesn't make as much sense as some of these. But we can really make all of these things happen, which means we have now access to higher efficiencies than we ever had before. And all with this notion of this low embodied energy and really rapid energy payback time, and the idea that we're going to be targeting at the module level these kind of places in the chart. So the last thing I want to talk about, and given the hockey stick that I showed you in terms of this climb here, right? The scalability seems to be there with the materials at a very basic level. So that leaves me with this question of the years of operation or the reliability, because this is an important thing in the context of this energy payback time and the EROI. The challenge is that I can fundamentally walk into the lab tomorrow. I can tell you the efficiency in 5 minutes. Telling you whether or not that particular device is going to be scalable, okay, maybe that takes a couple weeks or maybe a month. But to ask the question, for a device I make today, where will it be in 30 years, is a much harder question. And in the context of reliability, when we heat, one of my colleagues, she used to say, if you heat an egg a little bit in the incubator, you get one thing, but if you heat it in boiling water, you get a very different thing. And so, the notion of, say, doing stress tests or accelerated testing on PV technologies sounds really, really good, but it's a really, really massive challenge. And that's a lot of what we're doing these days, is to understand how some of the manufacturing that I talked about couples to what really the reliability is, and how do we find out very quickly what the reliability is. So the very last thing that I'll leave you with is, this is the stability of a solar cell that we made in the very first year of the project. And my project's been now going about 6.5, 7 years, something like that. So, but very quickly, this is all work that was done within the first year. So we made a device that was a little bit more stable. I mean, this was a pretty hot mess. Then we made some more modifications, and, we improved the stability a little bit more, and yet a little bit more, and yet a little bit more, and yet more. And if you look at the difference between here and here, that represents about a factor of 100 change in the stability. And we did that in about 2.5 years. And I thought we would still be working at kind of this stuff, but these days we're very much concerned with not what's happening indoor, but what's happening outdoors with these devices. What we see in the lab, I have to wait entirely too long to know whether or not I have any kind of defects that are going to cause a problem for the stability long term. And so we're doing more and more outdoor testing. And then finally, perovskites are a technology that a lot of people say aren't ready for prime time, but there are already out in the world demonstrations of stable perovskite solar cells over extended periods of time in outdoor operation at, efficiencies that are less than, say, what our team would aspire to, but are reasonably efficient nonetheless. And then finally, turning back to kind of the notion of where we are with PV technologies more generally, PV really is at a tipping point where we're in a position to start generating electricity with these clean technologies at a scale and size that really moves from a consumption to a sustainable model. And that means that we need to be thinking about things like end of life and other things for PV technologies like silicon, but also for incumbent or for kind of emerging technologies in addition to those incumbents like perovskites. And indeed, we've already done a lot of work for things like end of life for perovskite solar cells, and are increasingly doing more and more on some of the incumbent technologies as well, as they have a little bit more challenge. We've been designing from the get-go for the notion of achieving, say, terawatt scales technologies, which means we have to think about these things at the beginning in a way that silicon hasn't had to do, but is clearly what they aspire to do. So they're catching up very, very rapidly, since there's a lot of really high quality work in that technology as well. So I think that's all I got. So thanks. I hope it's been educational. I do have a little video that we'll let run. But this shows the magic of perovskites.
Methyl ammonium iodide and TBI2 in my magic solvent chemistry I've been working on. Now we're going to see if we can emulate Bob Ross. So I'll just take a little tree. Say that I work at NREL. And then for Bob Ross, we'll put a couple happy trees in here. Maybe a little sun. A little mountain shrub. Let's see, a little mountain. Sun.
So I think that makes the point. And that's a few years old now. You can find it on YouTube, but that ink will support kind of an 18% efficient device. It's one of the older ones. We've moved on from that, it turns out, but it still demonstrates kind of the promise. So that I'll take any questions if that makes sense.
Thank you so much, Joe. Chuck, are you and Joe ready?
I can try and find the...
I don't see the chat, but
yeah.
Just give me a minute.
Okay.
Sure, I can take the first one. Chuck,
Go ahead, Joe.
what in your opinion is the likelihood of adoption of the Build Back Better energy provisions in standalone legislation?
That's outside my lane, I'm afraid.
Yeah, I think we'll have to table that one. We could handle that at the end if somebody.
I would love to know the answer to that myself, if I'm honest. I mean, I'm a serial optimist. Well, in some things I'm optimistic, in other things, right? You know, as a scientist, you're paid to be pessimistic. But yeah. That's, yeah. My dad was a political science professor before he retired, so he's the person to ask on that one, I'm afraid.
Oh, we'll jump to the next one. Why did companies like Solar World, who used to make their cells this way by growing them in a lab and cutting them to put in their panels to sell, why did they stop making their cells near the end of their existence?
So, yeah, so if you look at people who are doing silicon based manufacturing, because of the energy intensity of that, right? I mean, it's expensive, both from a facilities perspective and from an energy perspective to run that facility, right? If I go back to this, this graph for this module, right? So this is, you know, 50% less energy intense, or pardon me, 50% less carbon intense than the equivalent module made in China. And some of my colleagues have some work that's hopefully going to be through peer review. I would have loved to have shared it if I had it available, but I think they're still working on it a little bit with the editors there and the reviewers. But basically, the CO2 intensity is less because it's manufactured in Europe, but that does make it a more expensive product, right? Similarly, if we were to manufacture in the US, the energy mix that we have is more expensive. It's cleaner, but it's more expensive. And it's hard to compete on pure price if a lot of your value proposition is the reduction in the carbon emissions, if you will, right?
Yeah.
So in other words, the price that you're going to have to pay for this module is significantly greater than the price you're going to pay for this one, even though, because there's essentially no carbon tax, if, for example, as one way to normalize that.
Yeah.
And that makes it very difficult to compete in the context of a U.S. market, because there are solar manufacturers in the U.S. like Hemlock and others, but if you're manufacturing silicon, there are a lot of other customers in the U.S. for silicon, like Intel and ADM and Texas Instruments, and those are the people you're going to sell your silicon to. You aren't going to sell it to people who are trying to make commodity products like solar. So that's a big challenge, right? And that's why, there are a lot of reasons that say are beyond kind of the nuts and bolts of the science of what has to happen to make the materials, where if from an economic perspective, there are some structural advantages that the central government of China has set up that give them an advantage in manufacturing and producing silicon that can be taken by people and made into modules at costs that are lower than what you could argue would reflect fair market value. I believe that's something that's been investigated by Commerce and others. But that's probably about as much as I can say while staying in my lane. I hope that answers the question.
Okay, we'll follow that up with another sort of green question. How green is the process for manufacturing solar cells compared to the fossil fuel industry?
Well, so the greenness of it really depends upon the energy mix that you're using, which is why this energy payback time concept is so powerful, right? So there are some places where, for example, with silicon, you will produce CO2 as a chemical byproduct of essentially removing. Silicon likes to be paired up with oxygen, and so if you're going to remove the oxygen away from silicon dioxide to make it into silicon, typically what you do is you bind it to carbon, so you produce carbon dioxide, right, as opposed to silicon dioxide. So you will produce some CO2, but fundamentally that's a much kind of cleaner process than any kind of fossil fuel. Not only that, right, after your initial energy payback, the rest of that electricity that you're generating from that module is completely clean and has no CO2 in it, right? So if, so the impacts to climate change from PV are massive. And I may have thrown this slide in here. If you think about it and reflect on it, it turns out, here's a graph. This is the global energy resource. This is from a center that was at Stanford for a number of years, and it's a little bit out of date, but solar radiation is the energy that we receive on the Earth. We convert that at really low efficiencies into things like biomass, and we, again, with low efficiency, turn that into coal, right? That's what happens on the planet. Now, we're essentially extracting this resource directly when we're burning fossil fuels, so we are in a consumption phase. And so the notion is that solar PV technologies, and specifically, provide us a way to stay up here in this loop without being in consumption, in purely consumption kind of phases, right? We can be in a sustainable, more of a use phase with our energy technologies, if you will. So it is fundamentally different. I hope that answers the question.
Thank you. So you want to get the next one, Joe?
Sure. For the outdoor testing, are you using full-sized models using perovskites?
So we are, at the moment, we are still using what we would consider to be relatively, say, intermediate sized demonstrators. So we're doing things that are starting to become the size of a piece of paper, so to speak. And that's, that allows us to test a lot of the things that we're interested in, but it's clearly, it's a necessary but insufficient kind of exercise. And we're funded by the U.S. Department of Commerce, or pardon me, U.S. Department of Energy, Department of Commerce. Where did that come from? U.S. Department of Energy, the Solar Energy Technology Office just did a piece in ACS Energy Letters where they kind of outline their portfolio. And, you know, that office really does a lot of work to tailor their portfolio so that they're touching all the bases. But for some of these activities, you know, it's much more capital and resource intensive. And we're trying to get to the place where those kind of investments can be made that really kind of help U.S. industry in a way that's meaningful. But we're doing, you know, intermediate size, but not full on modules like you would see from the likes of for solar. And indeed, that's reflected directly in some of the graphs that I showed earlier. If I can find it quick, I'll throw it up. Where is it? Yeah, if you look at this, right, with these colors indicating the size, a first solar module that they're producing or one of these Q-cell modules, I mean, these are really, really massive things. In contrast, right, you know, we're at this kind of small scale with our modules in this green area. And you can find this full data set at NREL.gov if you have a look.
Thank you.
Okay, I got the next one, Joe. When you speak about energy payback, are you considering only the energy payback of the PV device, or are you considering the energy payback of the complete operational solar PV system, which is the only thing that really counts?
So I would argue with the only thing that really counts, but the balance of systems costs are essentially something that is something that we do account for in the way that we look at it. And if you think about it, right, it turns out the paraphernalia that I'm going to use for a silicon module isn't different from the paraphernalia I'm going to use for a CAD-TEL module or a gallium arsenide module or a perovskite module. So in that sense, the thing that we really care about is the efficiency of the device, right? So the higher the efficiency of the device, the more you can offset those other costs, which we group into what we call balance of systems costs. Now, there's certainly room for innovation on the balance of systems costs, but those will impact all of the PV technologies in terms of the energy payback the same, right? And in that case, you could argue they don't really count in the comparison that I've done, but we do account for them. I hope that answers the question. And indeed, yeah, the energy payback times are typically calculated for kind of, you know, I mean, it can really depend on, like, that's also the reason why I've given a range, right? Because if you're a utility scale operation, your balance of systems costs are going to be different than if you're a residential solar owner, right? If you're a residential solar owner, a lot higher percentage of your costs are in those balance of systems components than, say, just straight up your module. Whereas for a solar plant, say, that's sited someplace, there are some economies there.
Sure. Okay. Joe, you want to ask him about the fan?
Sure. Is that a solar fan behind you?
No, it's just a regular fan.
Are there other questions? If not, I have one, Joe.
Okay.
Can I ask mine? Cadmium telluride. Cadmium is a heavy metal, right?
Mm-hmm.
You talk about recycling and you know, reuse and repurposing. Can we do that with cadmium telluride?
Yes. So cadmium telluride. Cadmium is a heavy metal. It's a heavy metal that makes lead, which is the basis of most of the metal halide perovskites that I've talked about here. Cadmium is much more toxic than lead, but it is bound up with tellurium, which means that it's not quite the same thing. Having said that, you don't want to eat either of them. Tellurium, on the other hand, is a material that's not terribly abundant in the Earth's crust. But And again, this is kind of the figure, but if you consider how much of that material I need in a thin film PV versus how much material I have in just by pure mass in a silicon device, that material is both precious and relatively sparse in the overall module, right? So the embedded energy for CAD-TEL is really dominated, and any thin film technology is really dominated by the energy that we use to make the glass for the front and back sheets of that.
Wow.
Yeah. And it turns out that for CAD-TEL, because the cadmium and tellurium are materials that, say, the supply chains are a little bit challenging for in some ways for various reasons. First Solar recycles at really, really high efficiency. They recycle at something like 80, it's north of 80% by mass. The glass gets downcycled, but the cadmium and tellurium, which are key components to their manufacturing, get recaptured for the most part.
And similar could be done for perovskites, right?
That's exactly right. I guess I had a slide, but I didn't actually get to it. We have looked, this question of, well, lead-free perovskites. Why do we not do lead-free perovskites, metal halide perovskites? And it turns out that lead is very special in the details of the electronic structure of the material in a way that we've done some work at looking at lead-free. That's not a tractable. Well, I shouldn't. You never say never, right? It may be tractable, but there's not much of a value proposition, if I'm honest there. Because the lead hazard that we're talking about, because the material layer is so thin, and lead is only one component, right? Remember the unit cell, if I go back, has got a lot of other stuff in it, right? The lead's sitting at the middle of this, all this other stuff. So the amount of lead in it is pretty small, and all the detailed studies that we've done, if you allowed all of the absorbent material to get kind of washed away into the ground, just doesn't create much of a hazard. So it's not really rational from a global perspective. But we don't want to create situations with a technology where we're not able to implement them in ways that are equitable and just, and where, say, communities that have financial challenges might be exploited. So there are easy solutions that we've been looking at and implementing to basically making sure that if one of these modules were to fail and, say, be cracked and rain were to come in, that we would grab up all the lead and it would still be contained in that module and it wouldn't be a spill hazard. And this is work that we published in Nature a few years ago where we show that. And these technologies are low cost and cheap. And given how hard it is to find a semiconductor that can do what these materials can do when they have lead in them, in terms of absorbing photons and changing them into electricity, these kind of technologies are far and away the place where I think research effort is best spent, if that makes sense.
Okay. We've got definitely some more questions, Joe. Are you
Yep.
up for a few more?
Oh yeah, yep.
All right.
Okay, have you seen or heard of hemp, HEMP, biomass being used for panels instead of silicon?
So not in the absorber, right? So silicon, I mean, again, for the primary absorber, you need a material that is really a semiconductor. You can't do it with a plant in the same way, right? So a photosynthetic kind of concept, there are ideas about using things like organics or bio-inspired materials to do that, but none of those are at the kind of efficiencies that kind of make a difference. The place where there are some things that start to become interesting are really in some of the module components. Let me go back here quick. Where's my module picture? Yeah, so if you look at your module, this aluminum actually takes a lot of electrical energy to produce, right? And that's indeed reflected in this kind of, oh, no, wrong way. this accounting, right? I mean, the frame is a pretty significant sink of energy and of carbon. So finding ways to do that with kind of structural materials like hemp or, kind of biocomposites that would be hemp and say woody plant-based is something that some people are starting to look at. As well as, the other parts of it. So I've worried about the frame, but I guess if I went back to this one, right, if you think about the stanchions and other components, again, there are opportunities there for those to be greener kind of products than, say, something like aluminum. Although aluminum is, could be worse because the recyclability is super high on aluminum. So once you've spent that energy to make it the first time, reusing it is a pretty tractable thing.
Okay. So there's another question around, I think it's 3D configurations of panels. Instead of a flat glass sheet, incorporating the equivalent of lenses to focus the light.
Yes. So yeah, there's some very interesting kind of concepts that one can use to basically do. All right. Let me try and address it this way. All right. So this tandem strategy here, right, really is essentially splitting up the light into different sections. There are a couple different ways we could think about doing that, right? Here, we just layer these different semiconductors on top. The first one takes all the blue, the second one takes the green, and so on and so forth. But you could really use essentially composite optics to basically split the spectra apart, right, like a prism does, and direct each of the colors to a different cell that's optimized for it. That's a strategy that people have used. In addition, you can also do kind of approaches that are more on the quantum side, where you take a single photon of a particular wavelength and you make it into, say, two longer wavelength, lower energy photons that can still be absorbed by your absorber, but then you avoid the thermalization loss. That's what we call spectral splitting. And there's also what we call spectral squeezing, which is to take two photons that, say, would have been too low energy to be absorbed, squishing them together, and generating a photon that's sufficiently high energy to again harvest. So those kind of spectral approaches are things that people are actively looking at, but they require that the efficiency of those processes be very, very high in order to have them make sense relative to, say, a multi-junction approach like what I'm showing here. And typically those light splitting approaches, say like the prismatic ones that I described, they have some optical losses that end up making it a little bit challenging. And the squeezing and splitting approaches have some losses that are more kind of fundamental, say, science challenges that people are working at. Making some progress. There are some concepts that I think are coming close to market that could really improve. It's what we call an optically coupled tandem type device, where your first layer really takes all the photons at the higher energies and converts them to lower energy photons at a higher number, and then you absorb it into your device. That's a strategy that people are playing with. Yes.
Okay. How about, can you hear me?
Mm-hmm.
Where is the development for 1/4-inch thick silicon solar PV cells?
A 1/4-inch thick?
That's what it says.
Oh, that's a.
I actually said quarter thick. I thought I've seen some publication of where they're going to cut wafers that are a quarter the current thickness.
Yeah, so this is a concept that people have tried a couple different times. The challenge has been not so much in doing it as doing it in a way that is highly manufacturable and scalable with high yield. So there were a number of companies that tried this a number of years ago, and that definitely creates some, I mean, it makes sense and it's rational, and it could basically lower your embodied energy costs significantly. One of the things about silicon as a semiconductor, though, is that you do fundamentally still need much more of it than you'd need of a lot of these thin film materials because silicon doesn't interact that strongly with light. So those thinner technologies and the hassle of the wafer handling is accompanied by a loss of efficiency that hasn't made them terribly appealing. However, in the context of a tandem, like the silicon perovskite tandem that I showed, because the silicon doesn't need to absorb as many photons, that starts to become an appealing kind of idea again. The question will be, can you really do the handling of those really, really thin wafers effectively in a way that enables you to make modules? It's an engineering challenge a bit more than a scientific one, if you will, but people are interested in that. And I have heard some rumors about companies who have ideas about it, but I would have to see the data and the yield. Like you could totally do it at a research level. Doing it at an industrial scale where you're doing gigawatts, I think, is the challenge. Does that make sense? And did I answer the question?
Mm-hmm.
I hope the answer is yes.
Yeah.
Thumbs up.
Okay.
So, Gordon, do you want to unmute and ask your question around energy payback rather than me trying to read this? Is he there? Gordon?
Yeah, I can read the question too. Right. So this was related to, unless are you unmuted, Gordon? Do you want to go?
I am unmuted, I hope.
Well, go ahead then. Go for it.
If you can hear me, thank you. I very much appreciate your comments about energy payback times because I'm in Alberta in Canada, and so we're always fighting with the coal and the methane gas electricity generation and about energy payback times. And I believe the Fraunhofer Institute in Freiburg, Germany did a really great study on energy payback time, which I think is in the order of two years or something. So I was very, very keen on hearing your comments about energy payback amongst different devices, yes. And I appreciate you're focused on the device level, which is awesome. But I'm focused on the engineering and competition with other energy forms. So that's why I wanted to know if your numbers included all the other incredibly components of a system, such as inverters and substations and cables and mounting.
Yeah. So yeah, at a system level, I mean, I guess the other part of the question becomes, and I'm not as familiar about what the economies are. Like I said, so from a PV perspective, the balance of systems costs are very comparable across the different technologies. The balance of systems costs for, say, a combined cycle, say, natural gas plant may be different. And that would be the comparison that you'd want to do in the context of trying to understand that energy payback and the CO2. I mean, the CO2 equivalent, right? Solar is going to win that based upon that graph that I showed of, the fact that basically everything is indirect solar. But you'd want to understand those balance of systems costs for those particular power and utilities in a way, and where there are differences versus what you'd have for a solar plant. I know that the reliability and resilience of what we call power electronics at grid scale is something that is actively being researched. Many people in the audience may be aware, right? You can now buy, say, chargers for your phone or your laptop that are based on gallium nitride or other wide bandgap semiconductors that are much, much smaller but have much higher wattage rating than the old blocks you used to get. So those kind of balance of systems costs are so miniaturizing in the context of power electronics is a big deal from an energy perspective in terms of the use phase. What the overall LCA and embedded energy economy of that looks like how long you have to use those systems to basically get your energy return on investment. I haven't seen detailed analysis on that, but my sense of it is that the energy consumption phase very rapidly exceeds the embedded energy cost in those systems. So efficiency is key. One analogy that I could make is the difference between, say, an incandescent and a solid state lighting light bulb, right? The embedded energy of those systems is so far outstripped by the use phase after about the first year that any efficiency you gain is kind of bankable, if you will. I hope that answers your question, but it is significantly more complex to do that kind of analysis, because those aren't necessarily, those balance of systems aspects aren't the generation component of it. So they aren't the thing that's doing the dividing, is the other way to say it.
I want to appreciate what you're saying. I guess from my perspective, it would take somebody to do an energy consumption analysis of the manufacturing of inverters and racking and substations, etc., and then just include that into the module energy consumption and divide it by the energy generation in order to get a system payback. The only payback information that I've seen for coal, for example, is some study from England that says its energy payback is 3.7 years compared to 2 years or so for PV.
Yeah, so the question would be there, what they're again, the devil is in the details, right? So it really depends what they're including in that. Is that really just the balance of systems and essentially the distribution costs? Or is that the cost for basically all the heavy manufacturing equipment that you need to basically mine the coal, right? I mean, fundamentally, coal can't have a, how should I say this? Something like coal is really just essentially pure consumption, right? So you can get more energy out than you put in to extract the coal, clearly, right? And that would be considered the energy payback. But at some level, that's distinctly, I guess, no, it is the same problem, I guess, but you'd need to basically account for kind of different sets of costs, right? The mining costs and all this kind of thing for the materials is something that's embedded in these energy payback calculations. And so my presumption would be that for, say, coal mining, you'd have equivalent kind of costs that are associated with it. But where you draw the line around kind of that system in terms of the distribution, you might be able to do it a couple different places. But you certainly could say, okay, well, if I'm going to burn coal, I need the boiler, and that's got to be included, just like I need the inverter for the solar cells.
Oh, yes.
But the details of the studies matter in that. And I tend to, for that reason, it's super nice when there are studies that do comparative analyses, because they can provide that. Doing cross comparisons between the similar technologies, this becomes very fraught, right? Because
Yes.
you can argue about whether it's fair.
Yes. Okay. I think, Phil, what do you think? Any more? Joe, are there any more questions? I don't think there are. Just congratulations. You did a great job, Joe.
Well, thanks again for the invite.
We appreciate you sharing your wisdom with us, and really appreciate all the efforts.